All right, welcome to IEC Indy's full-time program, lesson 202, part 1, standard service calculations for a dwelling unit. We're just going to jump right in. So, thank you for joining us. Lesson 202, service calculations. Branch circuit and demand calculations are requirements for determining service size and feeder size when wiring a one-family or multifamily dwelling unit. The NEC contains numerous examples of branch circuit and circuit service calculations in the back of the book in Y2 Annex D. So the NEC actually has for you some written down examples of different types of service calculations for you in the back of the code book. It's a great form of reference when you're working through service calculations to use that annex. So I highly recommend checking that out at your convenience. What exactly is a service? Well, a service is exactly what that picture is next to us. That is the connecting point between utility and the premises wiring on any building. Service, by definition, in the NEC code book is just that. It is the connection and the equipment used to connect premises wiring to utility wiring. And so exactly what then is a feeder? Well, if the service is connecting the building wiring to the utility wiring, then our feeder would be our service entrance conductors on the service side, or on the load side of our main disconnect breaker, it would be the wiring leaving our overcurrent protection and feeding our panel indoors after it's been protected by that main breaker. The definition of a feeder is between overcurrent protection devices and the service. And then a branch circuit would be anything past the last overcurrent protection device. So keep that in mind. What we're going to be focusing on today is we're going to be sizing this, and we're going to be sizing our feeders, feeding our service or feeding our main breaker. Why do we need to calculate anything to determine the size of an electrical service? Well, think of it this way. Whenever we hook up a piece of equipment, whether it be a motor, a furnace, an oven, you name it, any kind of resistive or inductive capacitive load, we always size it based on its rating or nameplate rating when it comes to equipment, determining or telling us just how many amps it requires to run that equipment. Well, when we build a house, our houses don't come with a little nameplate that says this house pulls 150 amps. Therefore, you need a 150 amp breaker to provide protection for this house. No, it doesn't say that. It's up to us as the electrician to figure out what exactly the rating of that house would be if it had one. So in order to figure that out, we need to calculate or add up the total wattage or the total volt amps used up in that house or in that structure to determine just exactly what that house is rated for and what size of service or overcurrent protection device we're to protect that house with. The NEC actually gives you a standard method and an optional method for sizing one family and multifamily dwelling units. Today, we're going to be focusing mainly on the feeder and service load standard for a one-family dwelling unit. Part 1 of the NEC Chapter 220 or Article 220 deals with general requirements for calculation methods. We're going to look briefly at that as well as Part 2 for load calculations for branch circuits. By this point, we've talked about these things a little bit in our previous classes, but today we're just going to kind of recall a little bit, refresh, remind ourselves exactly what the code has to say about certain things. Part 1, general requirements for calculation methods. Well, in 220.5, it gives us calculation parameters. In 220.5A, it actually goes on to give us boundaries. It gives us the boundaries, meaning that it tells us that what Article 220 applies to are any service or services with these voltages listed below. That could be 120, 122.40, which is a slash rated voltage, 208/120, 240, 347, 480/277, 480, 600/347, and 600 volts. So what that spells out for us, what their intent is telling us is these voltages, whatever service supplies these voltages, we can calculate that service based off of Article 220. And then 220.5b, it goes on to talk about the fractions of an amp. And I've highlighted this phrase right here, smaller than 0.5 may be dropped. Well, what does that mean? What that means is after we've calculated whatever the load may be on that service, or even along the process of calculating the load for that service, if we get a fraction of an amp, so I'm talking like 20 amps, 20.5 amps, well, at that point, I have the ability to either drop or round up that fraction of an amp. If it's smaller than 0.5, I drop it. If it's 0.5 and larger, I round up to the nearest whole amp. So for that example, if it was 20.5 amps, I would round up that calculated number to 21 amps. But if let's say it was 20.4 amps, that is a less than half fraction of an amp, I round down to the nearest whole amp. So it would be 20 amps instead of 20.4. Hope that makes sense to you. As we continue to move on through calculating our services and our feeders, keep that in mind because that will come into play with everything that you do from this point on when it comes to calculating your service. Part 2, branch circuit calculations. Floor area. Floor area we discussed in earlier lessons when we were talking about general lighting load. We will still be using floor area for our calculations for general lighting. Floor area is again the measurements of the livable space based on the outside perimeter. So whether that's living spaces, living rooms, bedrooms, you name it, the inside of the house. This does not include open porches. This does not include garages, crawl spaces, rooms that are parts of the building that were never intended to be used for human living. So those areas are not considered part of the general lighting floor area. So the other things that we have to keep in mind when we're doing calculations that are non-continuous loads, we're going to be calculating that at 100%. As well as our continuous loads, we're going to be calculating those at 125%. And just for your reference sake, what is a continuous load? I'm glad you asked. A continuous load is anything that runs for 3 hours or more. So if it has the intent or the potential to run for 3 hours or more, I'm sizing the circuit for that at 125%. So general lighting loads, 220.12. This was a change that they made in the 2020 code book. It used to be that dwelling units were part of Article 220.12, specifically Table 220.12. But in 2020, that got moved over to 220.14J, which is fine. That just leaves the Table 220.12 set aside for only non-dwelling units. So we're talking like exercise areas, firehouses, office buildings, stuff like that. But for today, what we're going to be discussing is not so much the non-dwelling units. Today, we're only going to be discussing dwelling units. And in order to get my general lighting load based on my floor area, I look to 220.14J, and 220.14J tells me that I have to multiply 3 volt amps per square foot. So that means if I have 1 square foot, it's worth 3 volt amps when it comes to my general lighting load. So if I've got a building with 1,000 square feet, I now have 3,000 volt amps applied to my general lighting load. I take my square footage, I multiply it by 3 volt amps per square foot, end up with my total floor area or my general lighting load volt amps. Now there's a permission later that we'll get into where we can apply our small appliance load and our laundry load when it comes to the demand, but we'll get into that here in a minute. When it comes to our receptacles in a general facility, I believe we're talking about anything not listed in 220.14J or K. Each of those receptacles is to be calculated at 180 volt amps per yoke. That's 180 volt amps if it's a single receptacle, very much like this guy right here. There's a single receptacle. That would be calculated at 180 volt amps on the service. Or if I have a duplex receptacle, this entirety would be 180 volt amps for that entire yoke. Not 180 here and 180 here, but only 90 per half, and it would be 180 for the entirety. So if I had a quad like this, it would be 180 per yoke. So that tells me I can calculate roughly how many receptacles, duplex or single, that I can place on a single branch circuit. Not only that, it also gives me the ability to calculate how many branch circuits I need, which also gives me the ability to calculate, especially in commercial buildings, a little bit more information on what the size of my service may be. Now, before we get into sizing the service for a single family dwelling unit, we need to talk about a term that's going to be brought up quite often when discussing calculation methods, and that term is demand factor. Now, the NEC definition for demand factor is what's written here. It's the ratio of the maximum demand of a system or part of a system to the total connected load of a system or part of the system under consideration. Okay, a lot of words there. Let's take what's in a little bit complex and make it simple. The ratio of the maximum demand of a system or part of a system to the total connected load of a system or part of a system under consideration can be just this. I have equipment connected to a system. The equipment connected to that system at its nameplate value may be a lot larger than what will actually be used because that equipment may not be running all the time. For example, ranges, electric ranges. I'm talking cooking equipment. Is the stove always going to be on? No. Is the oven always going to be running at full throttle 24 hours a day? No. The writers of the NEC understand that, and they know that there's no way that everything in an entire dwelling is going to be running at full throttle all the time. So they allow us to shave off some of the demand that the nameplate says that equipment runs at. So if the equipment runs at 11,000 watts, let's say I have an electric range that runs at 11,000 watts. The NEC gives us permission to not calculate in our overall service the entire 11,000 watts for that range, because it knows that we will never be running all the burners and the oven at full throttle all the time. So what they allow us in their table is to apply a demand. So instead of 11,000 watts added to the total wattage of our service, when we're trying to figure out what breaker size to protect the house with, we only have to add a portion of that 11,000 watts to our service. And we use the table found in 220.55 to figure out what that demand is, and the maximum demand for one range in that area would be, I think, 8,000 watts. So I'd have to look it up to be accurate about that, but let's just say it'll be 8,000 watts for the moment. That is the demand, or the ratio between what they expect us to use versus what we could use. That is the purpose of a demand factor. We are applying what they expect us to use versus what could be used at any given point. Because again, nobody leaves the lights on 24/7. Nobody has every outlet in the house plugged into something and it running 24/7. Nobody's leaving the microwave running 24/7. Nobody's leaving the TV, well, maybe the TV running 24/7. But you get what I'm saying. They're anticipating that in a living home where there's people in and out every day, not everything's getting used up to 100%. So they allow us to apply a demand factor, what we expect to use versus what we could use. So understand that going forward from this point on, when you hear me use the word demand or demand factor, know that we're shaving off from the total connected load the potential for using that entirety load at 100% all the time, because we know we're not going to do that. We know we're not going to use everything 100% of the time. So hopefully that helps you in understanding demand factor a little bit. Part 3, now we get into service calculations using the standard method found in Article 220, and we're going to start talking about right now one-family dwelling units. This is a single-family home. We're not talking apartment buildings. We're not talking condos and all that. We're talking a single-family house. Now, there are multiple steps. I call it 6 steps to sizing a house, or 6 steps to totaling my total connected load at its demand factor. Step 1, general lighting load. We find our general lighting load just like we talked about earlier with the floor area. We take that square footage of the outside perimeter of the livable space, multiply it by our 3 volt amps per square foot, and we also find that we are going to use 220.52 to include some other factors as well. Once we've added all of our factors to our general lighting load, we apply a general lighting demand. This general lighting demand is found in table 220.42, and we'll get into that here in a second. But that would be the completion of step 1, general lighting. Step 2, fixed appliances. Fixed appliances, or a better way of wording it, and I believe the NEC words it this way, is fastened in place appliances. Means that they are not moving anywhere. Like your dishwasher, your water heater, your sump pump. We're not just going to unplug our water heater or our dishwasher and move it into the living room because we like to watch the dishes wash. No, it's not a portable appliance. It's a fastened in place appliance. So that's going to, where 220.53 is where we're going to get our code references for calculating the total amount of fastened in place appliances in a general, in a single family dwelling unit. Now, be aware that there is a demand that is allowable or permissible according to 220.53, and that's if I have 4 or more appliances that are fastened in place, I can apply a demand of 75% instead of 100% to those appliances. And we'll get into that here briefly when we go over 220.53. 220.54, okay, so that was step 2. Step 3, 220.54, dryers, electric clothes dryers. We'll find that electric clothes dryers are not considered a fastened in place appliance. They have a demand all to themselves, and that's found in table 220.54 as well as 220.61. There's a demand on the neutral that we're allowed to place on that total connected load to our neutral, because it doesn't use a whole lot of unbalanced electricity or unbalanced power. So we don't necessarily have to include the entire dryer on our neutral demand or on our neutral load. So that's step 3. Step 4, electric cooking equipment, 220.55. Now, electric cooking equipment, like I said before, has a table that dictates or spells out, is a better word, I believe, the demand or the permissible demand that we are allowed to calculate our electric cooking equipment at. And again, Article 220.61 gives us permission to apply demand to the neutral load, because again, an electric range or electric cooking equipment has very little neutral load. A lot of their main power is found in the heating element, which has no neutral at all. Usually the neutral is only used for the small circuits within the range or in the dryer, like your light bulb and your fan, all the bells and the whistles that come with a dryer or an electric range. Maybe even the Wi-Fi adapter that helps alert your cell phone that your meal is done cooking or something like that. I don't know. But that gives us permission to not include as much as the entire range on that dryer or the neutral. That's step 1, 2, 3, 4. Step 5, heating or AC. I say it heating or AC, but it really ought to be spelled out a little differently. It should be called non-coincident loads or non-coincidental loads. What is a non-coincidental load? Great question. A non-coincidental load is something that is not likely or almost never or will never run at the same time as another load. For example, we use heating or air. The likeliness of your electric furnace running this at the same time as your electric air conditioner is limited. If your heat is running at the same time as your air, you have other problems to deal with at that point. So what they're really saying is, if it's not going to run together, if I have two pieces of large equipment like this, two pieces of large equipment like this, the likeliness of them running at the same time is very slim or none at all, then why do I have to include both of them into my service calculation when only one of them will be running at the same time? And if only one of them is running at the same time, size it to the larger of the two. If I size or include the larger of the two in my service calculation, when the larger one's not running, I'll still have plenty of room on that panel for the smaller one to be running. So that's a non-coincidental load. You'll find that in Article 220.60. And then 220.50, largest motor. Largest motor, 220.50 actually is a code that points you to some other codes, and one of that other codes that it points you to is 430.24. And in 430.24 it tells us that we need to, when we're sizing a feeder with multiple motors on that feeder, we size the largest motor at 125%. And then we include the rest of the motors at 100%. So what 220.50 is basically there for, it's there as a reminder to, hey, don't forget you need to add 25% to the largest motor on your service because 430.24 says so. So that brings us to a whole new level, especially with the whole non-coincident load, which we'll get into here shortly, because oftentimes the air conditioner in a one-family dwelling is the largest motor. And what happens if that gets omitted from the calculation because it was the smaller of the two loads? Well, we'll get into that. So let's keep moving forward as we plow into one-family dwelling standard calculation. All right, one-family dwelling general lighting. We've already discussed what our floor area is. Our floor area, outside perimeter, square footage, and then we apply a voltamps per square foot at 3 VA according to 220.14J, right? So we recalled that. 220.14J says 3 VA per square foot in a one-family dwelling unit. So 3 VA times whatever our floor area is gives us our total VA for general lighting. 220.52 goes on to tell us that we have permissions to include our small appliance circuits and our laundry circuits into our general lighting load. So our small appliance circuits, how many small appliance circuits are a bare minimum for a one family dwelling unit? 2. We find that in Article 210.11c, I believe. We are required to have at least 2 small appliance branch circuits in the home. And according to 210.11c as well, I'll have to double check my code reference on that, but according to 210.11, I'm required to have a laundry circuit as well. So that's 3 different circuits, 2 small appliances and 1 laundry that I'm including into my general lighting load before I apply any type of demand factor to the load. So what we've done is we've taken our square footage, we've multiplied it by 3 VA, and now we've added our small appliance circuits and our laundry circuits. Well, what's our small appliance and our laundry circuits worth when it comes to voltamps? I mean, it doesn't say in 210.11c how much power am I supposed to allot to them. Well, that's where I turn to 220.52a. And it says here 220.52a and b tell us that it's 1500 voltamps per circuit. 1500 voltamps per each small appliance circuit and 1500 voltamps for each laundry circuit. Now I can have more than just 2 small appliance circuits, but I'm at a bare minimum I have to have 2. So at the very least, I'm including into my 3 VA times my square footage 1500 voltamps for each small appliance circuit and 1500 voltamps for each laundry circuit. So a bare minimum of 4500 voltamps, 15 plus 15 plus 15 equals 45. 4500 voltamps on top of whatever the square footage times 3 is. That is where we get our general lighting load before we apply any kind of demand factor. Remember, demand factor is that ratio. We're shaving off some of what we of the total connected load to better represent what we expect to be using. And we find our permissions or the allowance in table 220.42 for our general lighting load demand factor. And if you turn to Article 220.42, you'll see that it spells out for us 3 different things. It says for us at the very top of table 220.42 that the first 3000 voltamps we're going to use at 100%. So I'm going to immediately take the first 3000 off the top. So let's say my total VA after I've calculated the square foot and after I've added my small appliance circuits comes to a total of 15,000 VA. I'm going to take all out of that 15,000 the first 3,000 and use that at 100%. So I set that off to the side here, 3,000 VA. That leaves me with 12,000 VA. Well, it says in the same table that anything between 3,001 and 120,000 I use at 35%. Well, that leaves me with 12,000. So anything between 3,001 through 120,000 looks more like a 0 now. Not really. It's going to be at 35%. So if I have 12,000 remaining and I divide that by 0.35, I'm sorry, not divide, but multiply that by 0.35 or take that at 35%, that leaves me with 4,200 VA. At that point, I add all that together for my total VA of, what is that, 7,200? 7,200 VA. That is my total VA for my general lighting load. That's how you calculate your general lighting load. And it also goes on to say, let's say, especially when we get into multifamily houses, this is where it's going to come into play. If I have anything greater than 120,000, I'm going to take that at 25%. So, and when we get to a video for multifamily dwelling units, we'll get into that a bit more than we will in a single family dwelling unit. The size of the service on a single family dwelling unit has to be pretty high in order to get into the 25% area of the demand factor. So that is step one, general lighting load. 3 VA per square foot, 1,500 VA for each small appliance, 1,500 VA for each laundry circuit, add them together, and then apply the demand factors of table 220.42. Do yourself a favor, kind of write down in your notes, earmark it, whatever you need to do, the demand factor table of 220.42. That's step one. Step two, fixed appliances or fastened in place appliances. Article 220.53. Article 220.53 pretty much spells out for us that we are going to take every fastened in place appliance, dishwasher, water heater, sump pump, attic fan, you name it. Anything that's a fixed in place appliance that doesn't meet a certain criteria. I think it's 300 volt amps and it's over 1/8 horsepower motor. That's what we're talking about here. I'm not talking about my bath fan and my shower. I'm talking strictly appliances that are a bit heftier than that. We're going to take those at 100%, whatever that appliance may be. No demand applied until we have until we have 4 or more appliances in the dwelling unit. If I have 4 or more, water heater, dishwasher, sump pump, attic fan, it doesn't take much to add up to 4. But if I have 4 or more appliances in a house, I can now apply a demand factor. So instead of using 100% of the nameplate value of those appliances, I can now use 75% of the nameplate value of those appliances. So I take those appliances, I add them all together, and if they have a neutral, I add all the neutral loads together as well. Not every appliance is going to have a neutral, and you'll know this based on the voltage. Remember to keep that in mind. If it's a 240 volt piece of equipment, not a 240/120, then it doesn't have a neutral. So keep that in mind. Add all of your appliances together, and if it's 4 or more, apply a percentage of 75% to it. Now on to step 3, the electric clothes dryer. According to 220.54, no matter what the nameplate value is, if it's below 5,000 VA, you're going to be including in your service calculation a minimum of 5,000 VA. So if I have an electric clothes dryer and it's only good up to, or its nameplate says it's only rated up to 4,000 VA, doesn't matter. I'm going to include a calculation of 5,000 VA at a bare minimal. Now, if the nameplate says something greater than 5,000 VA, maybe my nameplate says 6,000 VA, then I include 6,000 VA in my total accumulated volt amps for the power of that service. So what it comes down to, a minimum of 5,000 VA or the nameplate, whichever is greater. Nothing less than 5,000 VA though. After I have calculated the total number of dryers, I can then apply a demand factor found in table 220.54. Now, if you're just calculating a single family dwelling unit, chances are you're not going to need to use table 220.54. because according to 220.54, it says that if I have 1 through 4 dryers in a house, I'm taking all of them at 100%. So the likeliness of having more than 4 dryers in one house is very limited. Not impossible, but it's limited. Very small chance of that happening. So at this point, I just take it at 100%, minimum 5,000 or the nameplate, whichever is greater. And I add that to my service calculation. Now, according to 220.61, I do have permission to derate or to apply, not derate, that is the wrong word, apply a demand factor to the neutral on my dryer. Why? Because again, most of the load that dryer is going to consume is in a balanced heating element. It will have no unbalanced current, no neutral load, except for the minimal things like the dryer blower motor or the tumbler motor or the light bulb, the bells and the whistles and the chimes and the Wi-Fi indicator that says to your phone, hey, your clothes are done. All that's going to run on a 120 or lower voltage circuit. Then you'll have somewhat of a load on the neutral, but not at the full 5,000 VA. It'll be a very small version of it. So they give us permission in 220.61 to shave off our neutral load some of the expectancy that the nameplate says, because they know we're not using all of that power on the neutral. We're using it mostly in heat. So they allow us to take our neutral down from 100% down to 70%. So you can apply a 70% demand to the neutral. Step 4, electric cooking equipment. In order for us to apply a demand, again, that demand meaning the ratio between what's totally connected versus what we expect to use to our cooking equipment so that it safely is included in our service, is going to be found in Article 220.55, Table 220.55. When we turn to Table 220.55, go ahead and make sure if you're following along with this video and you have your code book out, go ahead and turn to Article 220.55, as we're going to take the next few minutes to really just kind of camp out on Article 220.55, mainly Table 220.55, when it comes to dealing with cooking equipment demand factors. The first thing I want to point out, at Table 220.55, at the very top, in the header of 220.55 table, it says at the very last sentence, column C is to be used except for provisions found in note number 3, or except when permissible by note number 3. The one thing I want to point out to you is in table 220.55, column C is a maximum kW allowance, meaning that is the total maximum in kilowatts I am expected to include on the service for the number of ranges that it may be representing. Whereas column A and column B are percentages. They're percentages based on the number of ranges connected to the load. Column A and column B are not permissible to be used except for note number 3, which we'll get into here shortly what note number 3 exactly means. But keep in mind, column C is a maximum kW rate. Now, table 225 at the very bottom has notes, has 5 sets of notes for you to be aware of. These notes are extremely important in using table 220.55. So as we move on from here, we are going to look at these 5 different notes and how they apply to table 220.55. First and foremost, I want to go back to table 220.55 and make sure you understand what you're using to apply a demand factor to your cooking equipment. So let's say you have one electric range, and that electric range is 9,000 watts. If I have a 9,000 watt range, the top of table 220.55 says I am to use column C in all cases except when permitted by note number 3. According to column C, the maximum kW rating, or the maximum kW allowance or demand that I am expected to include on my service calculation is 8,000 watts, or 8 kW. I now check to see if I can use note number 3. Well, I go down to note number 3, and before we get into note number 3, long story short, no, I'm not allowed to use note number 3 for one electric range at 9 kW. It doesn't meet the criteria. So I use column C, 8,000 watts. That's how many watts I'm going to include in my service calculation for that feeder and that service. Now, that being said, let's start working through the notes 1 through 5, and see how they apply to table 220.55. Let's start by looking at note number 1. Table 225, note number 1. Note number 1, if the range or ranges of the same size are greater than 12 kW, then use column C and increase the value by 5% for every kilowatt over 12. Now, I've taken what they've written and tried to simplify it to make it easier to understand, to show the intent of what the code's saying. And the intent of what this code is saying, what this note is saying, is use column C. But if you notice this, if you go to the top of column C, it actually says next to column C up to 12 kW. So what if my range is greater than 12 kW? Can I still just use column C? Well, yes and no. Yes, I can still use column C, but I've got to increase the number found in column C by 5% for every kilowatt that my range is rated at over 12. So up through 12, yep, I can use column C. That's my maximum output, or my maximum kW that I have to include in my service. But if it's greater than 12, then I take what I find in column C and I increase that by 5% for every kW that range is rated over 12. For example, if I have one range of 13 kW, it's a 13 kilowatt range, I'm going to increase the column C value of 8 kW by 5%. So then I take 8 kilowatts, or 8 kW, and I multiply that by 1.05. Now, why would I multiply that by 1.05? Well, at this point, we should all know that increasing it by 5% means I need to multiply it by 105%. Well, if I'm multiplying it by 105%, I'm literally moving my decimal over in order to create a decimal to multiply by. At this point along the program, you should be able to quickly move a decimal from one to another in your understanding of percentages versus decimals. So know that if you are multiplying it by 105%, I'm really multiplying it by 1.05. Or if it's 110%, then 1.1. 115%, 1.15, and so on and so forth. When it comes to the speed of calculating, especially on a master's test, you want to be able to take those, not shortcuts, but those avenues that allow you to accelerate faster and faster as you're working through these problems. It'll be only to your benefit. So 8 kW, multiply that by 105%, or 1.05, leaves me with 8.4 kW. I increased my column C answer by 5% for every kilowatt over 12. And since 13 is greater than 12 by 1, I increased it by 5%. Now, note number 2. Table 220.55, note number 2. If multiple ranges that are between 8 3/4 and 27 kilowatts, you can add the values together and average them up. If any ranges are valued less than 12 kW, then they need to be counted as 12 kW before you do your averaging. So what that means is, for example, if I have 3 ranges, and these 3 ranges are to be added to the service, and they value as the following: 10 kW, 14 kW, and 15 kW, what is the maximum demand for those 3 ranges on the service? Now remember, I'm allowed to add them all together and average them out. I mean, I divide it by 3. If there's 3 ranges, I got 10 plus 14 plus 15 divided by 3. But wait, I can't just add 10. Remember what it said in the earlier slide. It said if it's less than 12, then I need to boost that up to 12 before I do any averaging. I need to consider my 10 kW range as 12. So that 10 kW range, before I can add it to my calculations, before I can average it in, I have to increase it up to 12 kW. So it's 12 kW for that range, no longer 10. That's only in my calculations. So I take that 12 kW and then I add it to the rest. 12 plus 14 plus 15. Add those together, it gives me a total of 41 kilowatts. Now, in order to find my average, I have to divide that 41 kilowatts by the total number of ranges found on the service. And how many ranges do we have on the service? That's right, we have 3. So I take 41 kilowatts and I divide that by 3 ranges. So 41 divided by 3 ranges equals an average of 14 kilowatts. So I have 3 ranges averaged at 14 kilowatts each. So my next step then would be to go to column C, see what the maximum demand for 3 ranges is, look that up. Well, in column C, the maximum demand for 3 ranges is 14 kilowatts. And my average for my 3 different ranges is 14 kilowatts. So that being said, I can't just accept 14 kilowatts as is, because remember note number 1? If any range or any group of ranges that are of the same value are greater than 12 kW, because remember, column C only goes up to 12 kW. So if column C only goes up to 12 kW and my average is 14 kW, I have to take my column C maximum demand and increase that by 5% for every kilowatt greater than 12. And my 3 ranges averaged together is 14 kilowatts. That's 2 kilowatts greater than 12. So, just like it shows here, I'm going to take 14, take 12 away from it. That shows I have 2 kilowatts over 12. That means I need to increase my column C answer by 5% for every kilowatt over 12. And I have 2 of them. So I take 2 times 5%. That means I'm increasing my column C answer by 10%. So again, how do I do that? I take my 14 kW from column C and I multiply that by 110%. 110% or 1.1. I've increased it by 10%. That brings me to 15.4 kW total demand for all 3 ranges. That's how much I would include on that service for those 3 ranges. And that is note number 2. Note number 3. Table 220.55, note number 3. Remember at the very heading of our table here, it said column C is to be used at all times except for when permitted by note number 3. Well, here it is, note number 3. If ranges are smaller than 8 3/4 kW and larger than 1 3/4 kW, then it is permissible to use column A and column B percentages instead of the maximum found in column C. For example, let's say we have two ranges, and each of those ranges are only 3.5 or 3.5 kW. If using column C, then the maximum kW is 11 kW. We find that for two ranges in column C. That's my maximum demand that I am expected to place on the service. Now, if I just use note number 3, then I add my ranges together in their respective columns and apply the percentage of that column. In our example, we have two ranges, and each of those are rated at 3.5 kilowatt. So I can add those two ranges together because they're the same rating. Add them together, that gives me a total of 7 kilowatts. And then I multiply the 7 kW by the percentage found in column B. Now, why column B? I use column B because the ranges are between 3.5 kW and 8.75 kW. And that's what it actually says at the very top of column B. Column B is used for anything between 3.5 kW and 8.75 kW. And column A is actually used from anything from 1.75 kW, but not 3.5 kW, just between those two. So I take 7 kW and I multiply it by the percentage found from column B, which is 65%. That leaves me with a total of 4.55 kW. Now, column C said that we could use up to 11 kW, but because of note number 3, I have permission to use even less. I don't have to include that total of 11 kW in my overall service. I can go as low as 4.55 kW in the total demand for these two ranges on the service. Now for table 220.55, note number 4. It's permissible for us to calculate our branch circuits for one range using this table. And note number 4 also spells out for us that if no more than 2 wall-mounted ovens and 1 cooktop are on one branch circuit, then it is permissible to count them as one range if they're in the same room and use the table for sizing the branch circuit. So I'm talking specifically about 2 wall-mounted ovens and 1 electric cooktop, no more, and they all have to be in the same room. Then I can count all of those as one electric range, and then use table 220.55 to calculate what my maximum output for that one electric range, or that maximum demand is a better way of putting it, for that one electric range on my service, using note number 4. Or if it still falls within, after they've all been added together, if it still falls within note number 3 parameters, then I can use note number 3 as well. And then table 220.55, note number 5. If these ranges are used in an instructional program or a cooking educational facility, cooking school, then it is permissible to use this table to calculate demand for those ranges when sizing the service. Now, on to one family dwelling heating or AC, or a better way of putting it would be non-coincident loads. Remember, a non-coincident load is a load that will never run at the same time as another load. An example that we see more common than others, and especially in a home, is the heating versus air conditioning. Dwelling heating versus dwelling AC. If our heat and our AC are running at the same time, then one of two things is going on. We probably have a heat pump and we're using the wrong, we're not even allowed to consider this for the heat pump, or something's really gone wrong with the wiring and the heat is calling for AC at the same time as it's calling for heat, and something's really messed up there. So that being said, those two loads never run at the same time. So if I, according to 220.60, take the largest of those two loads and use that in my calculation, whenever that one's not running and the smaller load is running, I'm still going to be well within acceptable parameters on the size of the service because I've covered both of them by only claiming the larger of the two. That's because they'll never run at the same time. So, one last thing that was added to the non-coincident load, and this is a 2020 code change. If my air conditioner is the largest motor in the service, then it needs to be increased by 25% in my calculations. Now let's say that my largest motor is my air conditioner, and like 9 times out of 10, it's going to be the air conditioner as the largest motor in a home. It just usually is. So let's say my air conditioner, I have to increase by 25%. Yet, after I've checked it to see if it's the largest motor, and I increased it by another 25%, and it's still smaller than the electric heat, I'm still permitted to omit that air conditioner from my service calculation, and now I'm required, according to 220.50, and 430.24, to apply that increased 25% to the next largest motor in line. So if we've omitted the air conditioner, even after we check to see if it's the largest motor, then I go on to my next largest motor, whether it be a pump or a fan, whatever it may be, and I increase that motor by 25%. Because according to 430.24, we are required to increase the largest motor on a feeder by 25% and then include the rest of the motors at 100%, which we've already at this point included the rest of the motors with our fastened in place appliances. And if we omit, by omitting I mean removing from the calculation our air conditioner, then it's really no longer considered to be on the feeder because it was never calculated. So if it's the largest motor and if it doesn't get omitted, we increase it by 25%. If it is the largest motor and it ends up still getting omitted as a non-coincident load, then we move on to the next largest motor, whether it be a fan or a pump. And that we get out of 220.50 and 430.24. Now there's one more demand that we are allowed to apply to our service calculation, and that is the neutral demand. According to 220.61, we are allowed to apply a demand of 70% to anything on the neutral load after the first 200 amps. Now this is only for a single family dwelling unit. I'm not referring to commercial loads, I'm referring mainly to a dwelling unit right now. So the first 200 amps we use at 100%. So if you've done your calculations and your neutral load doesn't even come close to 200 amps, then you take everything at 100%, you're done. You've calculated what exactly is on the neutral load. Now, if you've calculated your neutral load and it's over 200 amps, here's where we're allowed to apply a demand found in Article 220.61. Article 220.61. The first 200 amps we use at 100%. So for this example here, the neutral was calculated and it came to a total of 216.67 amps. Great. According to 220.61, I take the first 200 amps at 100%. I set that off to the side. I've got 200 amps. That leaves me with a remaining 16.67 amps. That 16.67 amps I can now take at 70%, which means instead of 16.67, it's really 11.67 amps. Then I add those two together. 200 plus 11.67 leaves me with a total of 211.67 amps. That is my permissible demand allowed by Article 220.61, Section 220.61. After everything has been calculated, meaning we've calculated our general lighting, we've calculated our fasten in place appliances, we've calculated our electric clothes dryer, we've calculated our electric cooking equipment, our non-coincidental loads, our largest motor. After all that's been calculated and figured out, go ahead and add all those together. Add all those together to find our total VA for the load. Remember, our VA is, if we're looking at this through Ohm's law, VA is our P of our I equals P divided by E formula. We know what voltage is. Voltage in a house, 9 times out of 10, unless it's a multifamily dwelling, typically it's going to be 120/240 single phase. So 120/240, so 240 is our voltage. 240 is the E. Our total VA that we've calculated together is our P. We take P divided by E to figure out our I, and that is the service or the calculated load of our service. So let's say our calculated load of our service came out to 150 amps or 165 amps. Let's say 165 amps. Well, they don't make a 165 amp service breaker or main breaker. So now it is up to me as the electrician, understanding Article 240 and 240.4 and 240.6, that I can now size that up to the next standard size breaker, which would I believe be 175 amps according to table 240.6a. That would be my next standard size breaker up. I can't, if I'm over 800 amps, I can't use this rule, but because I'm under 800 amps, I can use this rule according to 240.4. So my next standard size breaker, 175. That means my main breaker for that service is 175 amps. That means I have 175 amp service. My total calculated load of that service is 165. My overcurrent protection device, or the size of the service, is 175. Now, we size our feeder conductors on one of two different ways. We size it based off of, first and foremost, we would size it based off of 310.16. That's our table for conductor ampacity, 310.16. I look at 310.16 and see what size wire, and I believe in the 75-degree column because this is an 100 amp or more service, and according to 110.14c, I'm supposed to consider that 75 degrees terminations unless it's listed otherwise. So 75-degree column, 165 amp wire or 175 amp wire. I looked that up, and that comes to, I believe, 2-aught. 2-aught, I believe, is good up to, I have to look this one up. 2-aught's good up to 175 amps. 2-aught's good up to 175 amps. Now, I have to compare table 310.16 with table 310.12. 310.12a and b give me permissions, as long as I don't need to make any kind of correction factors, permissions to reduce my dwelling unit feeder no less than 83%. However, and I believe I misread this in class the other day, so I'm going to correct myself here a little bit. However, at no given point is my conductor allowed to be sized smaller than the load expected to be upon it. At no point is the conductor allowed to be installed that is smaller than the load that is expected to be upon it. So, that being said, I compare 310.12 to 310.16. 310.12, if no correction factors are to be made, I look at the table and it tells me that I can install a 1-aught. Now I need to go back to Article 310.16 or Table 310.16 and compare that 1-aught and see if it's still going to be usable on that load. And I believe this is where I messed up the other day in class. So I want to correct myself here. In class, I said as long as it's 83%, I'm good to go. Doesn't matter. At no given point am I to install a conductor that has an ampacity less than the load calculated to be applied to it. And if we look up 1-augh's only good up to 150 amps. Table 310.12 says I can terminate 1-aught instead of 2-aught on 175 amp service. However, because it is less than the expected load on the conductors, or the calculated load on the conductors, I not necessarily have permission to use 1-aught instead of 2-aught. I have permission according to table 310.12, but I don't have permission elsewhere in the code where my conductors are not allowed to be sized any smaller than the load expected on them. So 2-aught would still be my overall service conductor. Now, if the load upon it was 150 amps, the calculated load, and I still went with 175 amp service, then maybe I could use 1-aught, because that means the calculated load would never get above the rating of the conductor. So know your difference between table 310.16 and table 310.12 and when to use them. Table 310.12 is only usable if the calculated load is less than or equal to that table. If the calculated load expected to be on the conductors is greater than that table, then the next size up, or according to 310.16, that's where I size my ampacity for my conductors. So for the fictional example I've been given of 165 amps, I would use a 2-aught, even though I'm landing on a 175 amp breaker. And I'm well within my code. I'm well within my parameters given to me by the NEC. And then real quick, I forgot to mention, when sizing the grounded conductor, the grounded conductor or the neutral is allowed to be downsized. It's allowed to be smaller than your ungrounded conductors, but it's never allowed to be smaller than that which is permitted in, I believe it's 250.102C1. So compare 250.102C1 with the expected load on the neutral. Whichever is greater, use that. And if it's greater than 250.102C1, then size the conductor based off of 310.16. Again, no conductor is to be sized smaller than the expected load to be found on that conductor. That being said, I'm a huge advocate for, as technology is changing, that we not downsize or reduce the size of our neutral conductors in the future, as we're seeing more and more nonlinear loads on the neutral, even in residences, as we include more and more fluorescent lights, LED lights. We're looking at more and more computer chargers, smart devices, computer terminals, smart TVs, smart refrigerators, you name it. All of these are increasing nonlinear loads on our neutrals. So I foresee, and I wonder, I just wonder, I'm not a code specialist when it comes to, let's just say there are a lot of people smarter than me out there. But I believe that in the future we'll see that reduction in the neutral change as our technology changes. Yet, for now, we still have permission to reduce the size of our neutral, so we're using less material. When I install a neutral, I install it the same size as my ungrounded conductors. So, but again, the code is bare minimum, right? Bare minimum for protecting people and for protecting property. That's what the purpose of the NEC code is. So I hope this video has been helpful for you. I hope that you have a better understanding of sizing a service calculation for a single family dwelling. Have a great rest of your day.